Right, for this section, this is 6.3, we're going to write and graph exponential decay functions. We were looking at growth functions in the previous unit because as we moved to the right on the graph, they were always increasing. Okay, we have the same format, so it's still y equals a, our initial value, times b raised to the power of x. A is still the initial amount in our equation, and b is our ratio, our constant ratio. When it's decay, that b value is going to be a value between 0 and 1. So whereas in the previous section we had whole numbers here that were greater than 1, you're going to see fractions there. And when we have a fraction there, you're going to see what happens here in a minute. It says write the rule for each function. So y equals some value. What's the initial value? Well, you want to look at what's happening at 0. What's happening at 0 in the table is 20, so that's the initial value. That's what it starts out at. Okay, and then you want to look and see what are we multiplying by to go up each time, or to go down, to go down each time. To get to the next y value, what are we multiplying by? Well, in this case, we're multiplying, it's going down by a half each time. It's getting half as big each time. So I'm going to say that my ratio is 1/2, and it would be to the power of x. So this would be my function rule. On example 2 here, to find my initial value, I want to locate what's happening at 0. Okay, what's happening at 0 is we have a 6, so that's my a value, and then times, and then to get my ratio, I want to see what is it doing each time in the y direction. Well, to go from 18 to 6, we're dividing by 3, but when we talk about this, we want to look at what are we multiplying by. So instead of dividing by 3, we can say I'm multiplying by 1/3. That's my ratio. Okay, and then we put our variable x is our exponent. Okay, so this would be my equation or my function for that. Okay, and if you want to write it in function notation, instead of putting a y there, you would just have f of x. So instead of using a y here, we would just say f of x. That's what it means by function notation. Okay, let's see what happens. When we graph the function, just like the previous example, we're going to make a table of values. So we're going to put in values like -1, 0, 1, 2, okay, and we'll see what happens. Okay, if I put a -1 in here, if I take a -1/2 and I raise it to the negative first power, okay, this goes back to our rules for exponents. What does a negative exponent do to a fraction? Okay, I'm sorry, this isn't negative, it's a positive 1/2. Okay, the negative exponent takes that fraction and flips it over. So this is going to become 2 over 1 to the positive first power, which is just 2. If I put a 0 in there for an exponent, 1/2 to the 0 power is still 1. Anything to the 0 power equals 1. And if I put a 1 in there, 1/2 raised to the first power is 1/2. And 1/2 to the second power is 1/4. Okay, so if I plot these 4 points on the graph, -1, I'm at 2. 0, I'm at 1. 1, I'm at 1/2. And at 2, I'm at 1/4. So now we're going to start high, and as we move to the right, we're going to get smaller and smaller and smaller. Again, I still put arrows on both ends of my curve, but notice as I'm going to the right this time, that value is decreasing, and that's why we call it decay. The value is dropping. Okay, if I make a table over here, table of values, if I put in -1, 0, 1, 2, if I put a -1 in here, that fraction 1/2 is going to flip over, and I'm going to have 3 times 2 over 1 to the first. Well, 2 over 1 to the first is just 2 times 3, I would get 6. If I made this 1/2 to the 0 power, anything to the 0 power equals 1, so that would be at 3. Okay, if I put a 1 in here, that would be 3 times 1/2. 1/2 to the first power is just 1/2. Make this into a fraction. I get 3 over 2, which equals 1.5. Okay, and if I put a 2 in here, 1/2 squared is 1/4. Times 3 over 1, this would be 3/4, or 0.75. Okay, so I'm going to do my best to graph those. Okay, -1, 1, 2, 3, 4, 5 is up here at 6. 0, 3. 1, 1.5. And 2 is at 0.75. So again, you've got this curve that's falling. Okay, it's going to curve around here and it's going to follow. It's not ever going to cross that x-axis. It's just going to get closer and closer and closer to it. Okay, if you want, you can use your calculator for the decimal, okay, or you can change that decimal into a fraction. Let's look at a couple of examples here. Well, actually, you can see that, so we'll do that. Where we had when we were talking about growth, we had this exact same formula. Y is equal to A. Growth, we had 1 plus R raised to the power of T. When things were appreciating or getting larger in value, that was growth, so it was 1 plus. The only difference with decay is now we don't add in. We're going to say 1 minus R. But we're going to apply the formula the exact same way. It's just now we take 1 and we subtract the rate. All right, so an example here, the initial value is 100. That's your A. So you'd say Y equals 100. And then in parentheses, I would have my growth factor is 1.05, okay, raised to the T. All of this, after you do the subtracting, that's called your growth. That's your decay factor in this case. When it was plus, so if it's Y equals A, 1 plus R to the T, this is your growth factor. Growth because you're adding on to it. When you're subtracting, that's your decay factor. So they're giving you a growth factor. We expect it to be greater than 1. So here's my function. Okay, here's a decay factor. So I would say Y equals 200. And then this is my decay factor. This is what I'm replacing here. So that would be 0.97 raised to the T. Okay, and now as soon as I give you amount of time, then you could plug in your time, and then you could actually evaluate that and figure out what that equals. Okay, and then here's a question. The number of acres of the ponderosa pine forest, it decreased. Okay, the fact that it decreased, or you might see a word like depreciation, that means it goes down in value. And if it goes down in value, you're going to use the decay factor. You're going to say Y equals A times 1 minus R to the power of T. If something is increasing in value or increasing in number, you use the growth formula. If it's decreasing or depreciating, you use the decay factor, or the decay formula. So it decreased from 1963 to 2002 by 0.5% annually. In 1963, there were about 41 million acres. So it says write a function that models the number of acres. So my function would be 41 million times 1 minus. Now keep in mind we have to take that percent and we have to change it to a decimal. So we take that 0.5%, and to get rid of the percent sign, we have to divide it by 100. When you divide that number by 100, that decimal point moves over 2 places. It's going to be 0.005, and we're going to raise it to the power of T. I would subtract this, so Y equals 41 times 1 minus 0.005 would be 0.995. Raised to the T. Okay, and then it says to the nearest tenth, how many million acres of ponderosa pine forest were there in 2002? So from 1963 to 2002, how many years passed? 2002, 1963. 39 years. So I'm going to raise it to the power of 39. Okay, and again, when you use your phone to do that, you've got to evaluate the exponent first. So I'm going to turn my calculator on its side. Okay, and I'm going to go 0.995. I'm going to raise it to the 39th power. And I'm going to take that decimal, okay, so you're going to get a decimal there. Don't round it, just take it times 41. And it says round to the nearest tenth. So I'm going to get 33.7, and it's million. Remember that 41 was million, so this is 33.7 million acres of pine forests are left. Okay? So keep in mind as you read the context of the problem, if it's growth, if it's growing or increasing, you want to use your growth formula. If it's depreciating or decreasing, you want to use your decay formula.